Chapter 12. In Chapter 12, we're going to look at inferences for population proportions. In this chapter, there are 3 sections, and we're going to cover all 3 sections. This lecture is going to cover only section 12.1, which deals with confidence intervals for one population proportion. Now, the word proportion in Chapter 12 means percentages. That's what that is. So when we talk about population proportion, means population percentages. That's what we're interested in. And you can also see here, I have highlighted the author's statement. The population proportion is the percentage of population that has a specific attribute or characteristic. And that's what we're going to discuss. So keep that in mind, that proportion means percentage. Now, here are some examples from your book. Any percentage you can think of. These are just some examples the authors made up again. So, for example, we may be interested in the percentage or proportion of U.S. adults who have health insurance. First example. Percentage of cars in the U.S. that are imports. Percentage of U.S. adults who favor stricter clean air health standards. And the percentage of Canadian women in the labor force. So again, it could be any percentage. We could, for example, say we're interested in the percentage of the students that are full-time and working part-time. So it could be any percentage that you may be interested in the population. Now, let's take a look at this. First, to our left here, sorry about that. I'm not sure what this is. Okay, sorry about that. So to the left here, we have, coming to this chapter, we talked about the means. The parameter was mu, and our statistic was x bar, a point estimate of that. So in chapter 12, our parameter is proportions now. The parameter is p. Now, a point estimate of that is going to be p hat. Okay, I know it's probably hard to see this, but that's what that is. This, what you see here, the symbol is p, and that's actually a caret sign or a hat sign on it. That's what this is. Now, the population proportion p is going to be, we have a formula here for it, x over n, where x is the number of items or subjects that have a certain characteristic or certain attribute that we are interested in. In this formula, again, for the population percentage, n, capital N, is the population size. Now remember, parameters of the population, and in this case, our parameter is going to be p, right in here. See, proportion, our parameter is p. These are unknown for us, and we need to estimate them. And the point estimate of this, of course, is going to be p hat, which is a sample percentage. Now, we are interested in inferences about the population proportion. And by inferences, we're talking about the 3 things that we've been consistently working with when we did inferences. One is point estimation, second is confidence interval, and hypothesis test. Those are the form of inferences that we are interested in. So first, let's talk about the point estimate. A point estimate means a single guess. The population percentage or proportion is the sample percentage or proportion. So the sample percentage, p hat, is given by little x over little n now. Little x is just like capital X, except it comes from the sample now. And of course, little n has always been our sample size and still is our sample size. Okay, now p hat turns out to be an unbiased estimator of p, and what do we mean by that? That means the mean, the center of its sampling distribution, is going to be exactly the parameter that we want to estimate, which is a good thing. We would like to have that. And here's just to paraphrase another way to say what an unbiased estimator is. That means if we take repeated samples of a fixed size, call it n, and for each sample we find p hat, the mean of all of these p hats will equal p. later on, we're actually going to verify this. We're going to do simulation online. There's going to be, I'm going to go to a site that actually does this simulation, and you will see that how this is going to work out. It's kind of like in chapter 7 when we did the sampling distribution of the sample mean. We went to StatCrunch and we illustrated central limit theorem. It's pretty much the same idea. Now, just to note that here the expected value of p hat, we also called it the mean of p hat. So we use those terms interchangeably. Okay, so this, what we're doing here is that this mu of p hat means the average of the sampling distribution, the average of all the p hats, right? The sample statistic p hat, the percentage from the sample for all possible samples, is going to be the percentage in the population we're trying to estimate. Now the standard deviation of p hat turns out to be this number. Now the derivation of these, it's not hard to derive these, but we're not interested in the mathematical derivations in this course. So, but this will give us the standard deviation. So far we have the mean, we have the deviation of the sampling distribution. What we don't have is the shape. Now, in order to do confidence intervals and hypothesis tests, we need sampling distribution of p hat. Okay. Now, the exact sampling distribution turns out to be binomial. Okay, but because it's difficult to calculate binomial probabilities, so we're actually not going to use the exact sampling distribution to do this. Okay, so what are we going to do instead? We're going to use approximate sampling distribution of p hat. Okay, now these approximate distributions, there's quite a few of them actually. I'm about to write down a few on the list, but there are more than this. So there are several approaches to finding these approximate sampling distributions. So some of these are the normal approximation, which we really like, right? Because we worked with normal distribution so much throughout the course. So we'll actually use this one. Now, this method of approximating the sampling distribution is called Wald method of doing the confidence interval. StatCrunch actually does this for us, so we will see this done in StatCrunch. Now this Wald here, by the way, this is named after Abraham Wald. The procedure is actually named after Abraham Wald, who was a statistician, and Abraham Wald actually was I believe he was a statistician during probably the mid-1950s. About that time, he was actually a Hungarian statistician, and unfortunately he died at the age of 48 in a plane crash. And if I remember correctly, he was flying over parts of India because he used to go on lecture tours. And on one of these lecture tours, he was flying, him and I believe his wife both passed in a plane crash. But anyways, so Abraham Wald, we're using this procedure and using normal approximation. Other methods are right in here. There you go. We have the adjusted Wald's approximation. There's Wilson score interval, Jeffrey's interval, Klopper-Pearson, Agresti, and Kuhl. Now this last one, Agresti and Kuhl, is actually, this one is available in StatCrunch. So StatCrunch actually gives us two ways of doing this, Wald, and the other one is going to be Agresti Kuhl. Okay, we're only going to be interested in Wald's. So which procedure is the best? It turns out that Wilson is the most accurate and robust of all the other ones, but there's also this one that's commonly called the gold standard. Klopper-Pearson also is sought out quite a bit. So as far as like, well, why don't we use these methods, the better methods? Because we have to sort of strike a balance between accuracy and also computational intensity. So for our concern, computational intensity takes precedence, okay, over accuracy. In other words, we're going to look at the easier procedure, okay, the easier of the ones that that I mentioned above. So we're going to go with the normal approximation, and here you go. So what this normal approximation says is that the approximate sampling distribution of p hat is normal with the mean mu p hat, which is equal to p and the standard deviation given by that formula. Okay, now this to get this sampling distribution, we assume that our random variable x actually is a binomial random variable, and as always we take a simple random sample. That's what SRS is, simple random sample with replacement, from a finite population, or without replacement from a population that is considered for all practical purposes to be infinite. So for example, I could have hundreds of millions of participants in the population. For us, that's infinite. Also, provided that the product of sample size n times p and n times 1 minus p is at least 5. Now, because we're not going to know p, we want to estimate it. So I'm just going to change that to np hat and 1 minus p hat for our work, okay? But again, the theory actually uses p. That would be a theoretical distribution that we use. But when we actually use confidence interval, we're going to change those p's to p hats. So there you go. And the sample size, of course, has to be large. Now, how large is large? Really, for proportions, we're talking about hundreds, maybe 200, 250, something like that. And as far as using this approximation, the product of np and 1 minus p, at least 5, that's large enough for us to be using this. And one note about this product, np 1 minus p times n at least 5, some other textbooks actually recommend that this product, looking at right here, np and 1 minus p. Some other textbooks and sources suggest that instead of 5, this should be at least 10. Some say at least 15. Some say at least 20. This author is going with 5 because although we don't cover chapter 13, the chi-square goodness of fit test, but in that chapter the assumption is that we have NP is also 5, so it's for that reason this author goes with 5, not 10, not 15, not 20. Now, this approximate distribution was actually discovered by DeMoivre and Laplace. Okay, and a long time ago at that too. It was 1812. That's when it was discovered by those mathematicians, both French mathematicians, Abraham DeMoivre and Pierre-Simon Laplace. Okay, and also I just want to point this out that most literature suggests these products that we just talked about to be at least 10. Some of them actually suggest 15, some suggest 25. So anyway, be flexible is what I have. For us, 5 is what we're going to go, and there you go. This is the approximate sampling distribution. Okay, and we're going to use this distribution for our work. Okay, now before we actually look at the confidence interval, let's take a look at, I'm going to go to the site that actually does a simulation of, there you go. So what we want to do is kind of like, again, what we did with the StatCrunch. We want to generate the sampling distribution of p hat. Okay, so here's the population we're sampling from, 0.1, and sample size is 50, not large. So just to show you, generate one sample, and I did, and right in here, you see that. So suppose I went to my population. Let's say 10% of the people in the population show allergic reaction to penicillin. So there you go. I went to that population. I sampled 50 people. In my sample of 50 people, the average sample proportion, 8% showed allergic reaction to penicillin. So that means 8% of 50, 4 people. 4 people in the sample. Now remember, the percentage in the population, the true percentage, which nobody knows, is 10%. And there you go. So that's sample p hat right now is 0.8. And then you generate another sample. Oops, sorry. Let me reset. I spoiled it for you. And there you go. So I can repeat this, right? Generate samples. And this is how we derive the sampling distribution. You take repeated sample of the same size over and over and over and over. So far, based on however many times I've done this, look at up here. The percentage in the population, average proportion, that's like mu p hat. 0.103, very close to the population. And the standard deviation is 0.037. Now, this standard deviation actually, we can find this using that formula, square root of p times 1 minus p over n. If you do square root of 0.1 times 0.9 divided by 50, you should get, let's see, I did, and I got 0.042. So this number is going to grow to 0.042. And let me now just generate all samples. Boom, there you go. Now notice the shape of the distribution. I know there are gaps in here, but the shape is almost kind of normal-ish. And look at the standard deviation, 0.043. Look at the average proportion. That's mu p hat, 10%, which is exactly the population proportion we want to estimate. So now let me change. Okay, p is small, but I'm going to increase the sample size. Look at that, to 1,000. So I'm going to take 1,000 subjects, the very large sample. Then you can do one at a time. Okay, you can do that, or generate all possible samples. Look how much more normal this distribution is. The average sample proportion, again, the center of the distribution is going to be 0.1, which is the parameter we are estimating. Now, I'm going to change that percentage in the population, this time to 0.5. Okay. Remember, for binomial distribution, if p is 0.5, the distribution becomes symmetric, right? And I'm going to change my sample size to back to 50 again, and one sample. Second sample, and so on. And here's all possible samples. And if I just keep hitting generate all samples, notice the sampling distribution is changing, right? Because I'm just generating lots and lots and lots of samples. So it's like the idea of infinitely many times. So I'm doing over. And look at the average sample percentage, 0.5, same as population. The standard deviation, 0.7. Now let me change the sample size to 1,000, and look at that sampling distribution. Very nice, almost normal distribution. Again, the same, the center of the distribution, same as the parameter. And finally, let me change that to 0.8. I'm going to sample from a right skewed distribution. So we did left skewed. I'm sorry, we did right skewed already. That was 0.1. Then we did sample from binomial where p is 0.5 and now 0.8. And if I look at, there you go, all samples. So we're actually looking at this. And if you look at that, the sampling distribution is almost normal. And there you go. I'm just taking repeated samples of the same size, 1,000. And distribution is almost normal. Again, the center of the distribution, 0.8, same as the parameter we want to estimate. Anyhow, okay, so let's go actually back to my notebook now, and now we are in a position to do our confidence interval. And that's all we're doing in this section, so it's going to go pretty quickly. This is going to be a brief lecture. It's not going to be too long. Now, we want to do a what we call a 1 minus alpha 100% confidence interval. This is a large sample confidence interval, Wald's confidence interval. Okay, that's what we're doing. And our assumption, again, we have simple random sample. Now this product of NP, by the way, if you look at here, and this is what I have. See, I'm over here now. Remember, P is P hat. This should be, right? This is P hat, right? P hat is X over little n. So this is going to be NP hat, right? Now, and n times 1 minus p, if I distribute the n and work this again, np again is x. So this is going to give me n minus x now. And you can change these with p hat also. Everything is p hat. Okay, so what's the point? One way we can check our assumption is this. You look at the product np. If that product is at least 5, and the product n times 1 minus p. If that's also at least 5, then we can go ahead and do this. Or instead of looking at np and n times 1 minus p, you simply look at the number of successes and number of failures. That's what that is, right? X, the number of items having the characteristics. So this is going to be our success. N minus x is going to be the number of failures, right? Both of those must be at least 5. Sometimes it's easier to just look at those two numbers as success failures rather than NP. However you do it, there you go. The formula is p hat plus or minus z alpha times sigma p hat, which is what's under the radical sign, the whole radical sign, and what's under it. What's to the right of plus minus is the margin of error, same as before. And having the margin of error now, we are in a position to actually answer this question. How large a sample do I even need if I want to estimate any population percentage? Like, for example, I want to know what percentage of people default under student loans. Okay, how large a sample do I need in order to make that estimation? Well, the answer actually lies within the margin of error. So I've reproduced the margin of error here. Okay, now if for those that are interested, feel free to follow what I'm doing here, but what's highlighted here, this is the formula we need, but we're going to that towards that formula. So in the formula for margin of error, this formula, we want to solve for n. So we're going to do a few algebraic steps. So what did I do first? I divided both sides of this equation by z alpha over 2 to isolate the radical, and I did. That's what I have here. Next, to get rid of the radical, I squared both sides, and that gives me this step. And then what did I do? I flipped the fraction, and this is what I got. I flipped the fraction on both sides, and then multiplied both sides by p hat 1 minus p hat, and this is what I got. So notice this is how we isolate for n or solve for n. Now, and that leads into this formula. Now, something interesting here, because remember, we're actually collecting a sample to estimate the percentage. In order to get our sample, this formula requires that we know p hat. This. Now, that's exactly what we want to do. We want to estimate p using p hat, but this formula requires that we know it. So it's kind of an ironic situation here. So at this point, there are a couple of remedial actions, well, 2 or 3 or maybe more even, but here are some of remedial actions we can take. We can estimate the percentage that we're looking for from maybe a previous study. Somebody else has done it, or we can simply guess if we have a good guess at what it should be. So the author suggests that we use subscript g, that means a guess value of p. That is simply a prior estimate. That's what that is. That's a prior estimate. Okay, that's p hat subscript g, some prior estimate. So that's one way of doing it. Another way is to actually don't make any guess, and I'll show you how that works. So what if I don't have a prior estimate, which is the question I have directly in front of you? What if I don't have a prior estimate? I don't have a guess here. Well, not having a prior estimate, we're going to look at the mathematics of how p hat times 1 minus p hat works. So now taking you back to your algebra days, for those that are still in line with their algebra, if you multiply p hat times the binomial, we're going to get p hat minus p hat squared, right? And that is this expression right in here. Now, this gives you a parabola. Remember the general form of parabola, it looks like this. So we went ahead and swapped out the p hat squared and p. And this is what I got. Negative p hat squared plus p. So it looks like a quadratic function. And now if you graph this quadratic function, the maximum of this quadratic function, that is p hat 1 minus p hat, happens when p hat is 0.5. Okay, that's the maximum value of p hat. This is p hat right in here. Okay, sorry, my pen is not working. Okay, it will work in a few minutes. So this is the maximum value of p hat 1 minus p hat. It actually happens right up here. See this 0.25? That's the maximum value of it. And it happens right in here. There you go. And this is p hat and this is 0.5. That's the maximum. And the maximum is 0.25. Okay. So what we're going to do is actually we're going to use 0.25 here. Okay. We're going to use that number instead of this product, which is p hat g minus 1 minus p hat guess. The most this can get is 0.25 this product can get. So why don't we replace it? In other words, that's the worst case scenario. So why don't we actually do that? Why don't we replace that product with 0.25? And doing that, we're actually going to get this. Next step is the manipulated version. So I went ahead and plugged in for this product, replace it with 1/4, that was 0.25. This is what it's going to look like. What I did next, I moved 4 inside parentheses with e, but this becomes a 2 now. The reason because of a squaring. See that 2 squared? 2 squared gives you 4. And there you go. We have a new formula. And this formula is going to give us what we call a conservative estimate of sample size. It's called conservative because we're looking at the worst case scenario for that product. The product in our research, in our work, may not be, in other words, as high as we think it is. So in that sense, it's conservative because it gives us more than what we need. But with sample size, you can never have enough. The more the merrier, the better. Okay. So there we have that one, and let me erase this one. So, and with sample size, remember we always round up, correct? Right in here, we always round up. No matter what the decimal is, you always round up. So let's take a look at one example here. We use this formula. So in this exercise number 23, we're just looking at people that buy things online. Okay, so well, this looks at, let's see, a sample of 603 interviews were conducted among a national sample of adults with household incomes of at least $150,000. Of the adults interviewed, 410 said they had purchased clothing, accessories, or books online in the past year. And what we want to do is actually, we want to find a 95% confidence interval for the proportion of all U.S. adults with household income of at least $150,000 who purchased clothing, accessories, or books online in the past year. Okay, so that's what we want to do. Now, our assumptions here that we have a simple random sample from the population. And what is our population? Right in here. Adults with household income at least 150,000. So let's say if we are not in that income category, then this does not pertain to us. They have a certain target population that they're researching about. And our random variable x here is the number who shopped online, of those people in that income category who shopped online. And our sample size is 603. We are given up here that information, total of 603 interviews. And x number of success here is success is if somebody actually shops online. 410 successes in this exercise. So now checking the assumption, remember the number of successes, number of failures must be at least 5. So x, the number of successes, 410, definitely bigger than 5. 603 minus 410, that is n minus x. That's 193. Again, that's also greater than 5. So the assumptions are met. We can proceed with this Wald's confidence interval. Now, what is P here? Just want to clarify what it is we're doing. P is the percentage of all U.S. adults with household income of at least 150,000 who purchased clothing, accessories, or books online in the past year. That's who our target population is, the percentage of those who actually did that. A point estimate, a single number guess at that, is going to be p hat, and that's what this is. That's our point estimate. It's going to be little x over n. So estimate of the population is actually in the sample 0.6799. Okay. And this is the sampling distribution, right? Approximate sampling distribution is normal. P hat is about 68%. That means 32% do not, right? That's 1 minus P hat. They do not purchase those things online in that income category. Now, our confidence interval, they wanted 95%, right? So that means our alpha is 0.5. That's our alpha 0.5. Half of alpha 0.5 is 0.25. And the z of that is 1.96. Now, how did we get this number? I just put a reminder. We did it in chapter 6, chapter 8, chapter 9, chapter 10. So you've seen us doing that before. That's the table value. And next, I'm going to actually go to the formula and construct that confidence interval. It's just a matter of plugging in the numbers and doing the arithmetic. So I did my p hat, plus or minus. Here's the z from the table, 1.96. And this part of it, that's sigma p hat, remember? Or an approximation and estimate of that. Square root of p hat, 1 minus p hat, divided by sample size. And just the radical ends up being 0.18998. This is if you want to check my computation. And then I multiply that number, of course, by 1.96. And this gives me the margin of error. Almost 4% margin of error. So what does that margin of error tell me? So we estimate approximately 68% of all adults purchase those things online in that income category. 68%. That estimate of 68% is off by no more than about 4% in either direction. So that's what the margin of error tells us. It's the give or take of our estimate. And we can build our confidence around the margin of error. And there you have it. So we believe with 95% confidence, we believe in the population, anywhere from 64 to about 72% of people purchase things online. Yes, this would be good information for marketing purposes. Okay, and I have kind of written what this statement means here, that we are 95% confident that the true proportion or percentage P is somewhere from 64 to 72% again. Okay, now this is what StatCrunch does. And I'll show you in a moment. We go to StatCrunch and you'll follow along with me. But just want to show you, see the lower limit, 6427, 6427, 0.71717, 0.7171. So they're pretty close. And this number, you see that? 018997, the standard error. That's actually your sigma. This is a sigma p hat. It's an estimate. It's an estimate of that. It's the standard deviation of the sampling distribution of p hat. And that number, I had it up here. You see that? 01. So that's what that is. And that's the square root. Okay. And we're good with this one. Now let me go to StatCrunch, and we're going to actually do this in StatCrunch, correct? So remember the numbers that we had. Let me copy these numbers down so I have them. So sample size was 603 and 410 number of successes, and our confidence interval was 95%. That's all we really need, right? And I'm getting the numbers from here. Okay, let's go to StatCrunch. So this is where I'm at in StatCrunch. So to do this, we're going to go to Stat, and then we go down to Proportion Stats. Now, in all of Chapter 12, we are only in Section 1, but the balance of Chapter 12 also. Let me show you something. Well, in Section 1, we have one sample, right? Later, we're going to have two samples, but for now, one sample. Now, in all of Chapter 12, any section, you're going to have summary data. You're never going to see all of these, the actual raw data. So it's always going to be summary data for Chapter 12. Okay. And there you have it. Let's click on it. And you see there's not much in here. The interface is asking for number of successes. Successes were 410. And number of observation, that's your sample size. That was 603. And we're doing a 95% confidence interval. And right in here, folks, you see that? Standard confidence interval, the standard Wald. Now, it's called a standard Wald because remember, if you go back and look at my notebook, you see that I had also in my list of other approximations, we had adjusted Wald. This is not an adjusted Wald confidence interval. This is the standard one before any adjustments are made. And then just if you click here on this arrow, it gives you the other option. See, aggressivity and cool. This is also an option that was in the list of options I had for you. But again, you don't need to check that one. But nevertheless, StatCrunch make these available. So I'm just going to stay with the default and hit compute. And there you go. That was it. Pretty simple, right? And you kind of see these are the numbers I got earlier. Okay, so that's how I got them. And hopefully that was easy for you to follow. Now, let's take a look at another example. Okay, in this exercise, this is one about the sample size. Okay, so that's all with the confidence interval. We're done with that one. Hopefully you can do what we just did. It's not complicated, not difficult if you just use the formula. Now, in exercise number 37, it reads, a company manufactures goods that are sold exclusively by mail order. The director of market research needed to market a new product. So they want to market a new product. She planned to send brochures to a random sample of households and use the percentage of orders obtained as an estimate of true proportion. Remember, when it reads true proportion like it does here, see that true proportion is what nobody knows. And that's what we mean by P. That's true proportion, known as the product response rate. So you want to know what the product response rate is. to that to the brochures. Okay. The result of the market research were to be utilized as primary source for advanced production planning. So the director wanted the figures she presented to be as accurate as possible. That's just the introduction to the problem. Now, specifically, this is what we want to do. She wanted to be 95% confident that the estimate of the product response rate would be accurate to within 1%. Without making any assumption, determine the sample size required. Now, here, what does he mean, the author mean by without making any assumptions? Without making any assumption, that means in part A, means we don't know, we don't have a guessed or prior estimate of P. I'm not going to say, well, suppose 20% are going to respond. Your response rate is going to be about 20%, 15. In part A, it says don't do that. So if I don't do that, then I have to use what the conservative sample size, don't I? If I'm not allowed to make a prior estimate. So that's part A. For 95% confidence, alpha is 0.5, half of that 0.25, and again the Z of 0.25, 1.96. Now, she wants the response rate to be accurate to within 1%. That within 1% is a margin of error. So there is your E, within 1%. Make sure you use decimal here. Don't use 1. You have to use a percentage or a decimal. You convert your percent to decimal here. Here's a formula, simple and clean. So Z is 1.96 divided by 2 times 0.1. You square it. Look at how large of a sample she needs. 9,604. She needs to get back 9,604 responses in order to be able to do what she wanted to do. Now, that seems pretty hefty and maybe not attainable, and that's what brings part B now. In part B, historically, product response rate for the products sold by this company have ranged anywhere from 0.5%, not much, to 4.9, almost 5%. If the director had been willing to assume that the sample product response rate for the product would also fall in this range, find the required sample size. Okay, so again, assuming the percentage is somewhere in here, this is your P hat guessed. That's what these numbers are, your guessed percentage in the population. How large a sample does she need? In other words, they're making the assumption, for example, that only about 5% is going to be the response rate. But that's what they want to find out. What is the response rate? So for part B, between 0.5%, 4.9%. So I chose P hat guess to be 0.049, the larger of the two numbers, the higher of the two numbers. In here, the higher of the two percentages. And the reason is this, to the right. If you look at the product right in here, or in here, okay, if you look at this product, 0.005 times 0.995, that gives me 0.005 almost, but 0.49 times 0.951 gives me a higher percentage. Higher percentage means greater sample size in this formula. Because look, this number is bigger than that. And this number, the bigger number, is exactly what goes in here. You see that? I have it right here. So I'd rather use the larger number that gives me the greater sample size. Again, with sample size, the larger the better. So that's what I did, in fact. And that is what I have here for the rest of the computations. So I still have 1.96 divided by 0.01 squared times that product. And this time, notice, by the way, the number to the right of decimal is 0.15. So she needs a sample size of 1,791. What a difference, huh? Going from almost 10,000, 9,600, to almost 1800. So wow, that's about almost 7,000, right? Well, almost 8,000, 709,000 fewer subjects. And there you go, by making that assumption. So and this part StatCrunch doesn't do. For the sample size, we need to use our formulas or ourselves. And there you go, we are done with this section. So again, the takeaway from this section was the formula that we had right in here, that formula that we had for confidence interval. And of course we had two formulas down below for sample size, right? Actually up here maybe, yeah, we had these two formulas. We had this formula and we had this formula for the sample size. Okay, so those are the three things we had in this section. So hopefully again you followed the video. If not, please go back and look at it again, review, and hopefully you'll be able to follow along the second time. Okay, with that we are done with this video.